Hello, welcome back to this course on tectonics and geodynamics. It's time for lecture 15 when we talk about finite and infinitesimal rotations and absolute plate motion. So this would be the title of the lecture that we're going to, the topics that we're going to discuss today. Okay, so the fundamental concept that we're going to be dealing with would be the concept of finite versus infinitesimal rotations. Now the word infinitesimal here is used in varying senses. Sometimes people use different words for infinitesimal. So sometimes the word used is incremental. So interchangeably, people have used the word incremental, or they've also used the word instantaneous. So they all effectively mean the same thing in this context. Yes. The only issue, of course, to remember is that since we're dealing with geological timescales, instantaneous here can actually mean tens of millions of years. So at least tens of millions of years. So the context in which this comes in to be important is because of the movement of plates on the surface of a sphere. So we've been talking about motion on the surface of a sphere. That is what plates do. So therefore, it is important for us to be able to understand, right, the differences, the intricacies of finite versus infinitesimal rotations. So let's just get back to the context that we were discussing all of this in. So whenever any object moves on the surface of the earth, right, we talked about the Euler's fixed point theorem serving as the basis on which we actually try to evaluate how movement would take place. So the idea is, of course, that if any point moves on the surface of a sphere, its movement is equivalent to that of a rotation about a fixed about an axis that passes through the center of that particular sphere. So we would treat it that way. So essentially, all motion on the surface of a sphere is in the form of a small circle. It can be a great circle when it is equatorial with respect to the axis of the Euler axis of rotation. Otherwise, in all circumstances, under all circumstances, the motion of any point on the surface of a sphere is going to be on a small circle with respect to that imaginary Euler axis. Now, we have been given, what we discussed before was that given the Euler poles of locations and angular velocities of relative motion between a set of three plates. So you have plates A and B, for which the Euler pole between plates A and B, the location of the Euler pole, as well as the angular velocity for the motion between plates A and B is given. And we've also been given the location of the Euler pole of rotation as well as the angular velocity of the motion between plates B and C. Is it possible, we saw that the question we asked was, is it possible to then calculate the Euler pole of location and angular velocity between plates A and C? And as we saw in the last class, we can do it. We can do it in various ways. We can solve it vectorially, but one of the things that we tend to do is actually to make it simpler for us, we use Cartesian coordinates because it involves only simple trigonometry. And we saw that you can actually find out the location of the Euler pole of location. You can actually determine the angular velocity. All of these things can be done. So essentially, it's a technique that can be used to reconstruct the motion between all plates with respect to each other. And that is how it has been done in the past. So again, this is taken from last lecture slides. So at Saft, Demetz et al. And you can see these define the poles, the positive pole, right? The pole from which viewed from outside is anti-clockwise in nature. So from all of these cases between Africa and Antarctica, this is where the positive pole is located. Between, say, Africa and South America, the famous one that people used so many times, right, to talk about the match on either side of the Atlantic. So in this case, you can see that the location of the Euler pole is it's almost near the Arctic Circle, right, and it's at a longitude which is 39.4 degrees west. Now these estimates vary from time to time, but nevertheless it means that we can actually calculate the positions of the Euler poles of rotation and the angular velocities for all pairs of plates that we know of. Now the advantage of this is that we can then calculate from this knowing this, we can calculate the motion of any point on a plate boundary between any of these two plates. The advantage of using the method that we used in the last class was that once we can apply that principle of finding out the Euler pole between location of the Euler pole between two plates whose relative motion with respect to each other was not known perfectly precisely before, we can use that to calculate, is because based on that then we can calculate exactly what the velocity, the linear velocity and the direction in which one plate is moving with respect to another can be along any plate boundary. So, this makes it possible for us to unravel the whole system. Now, it also gives us an interesting idea. So, if this is how a plate is moving, so if one plate, this is fixed with respect to another plate and it's moving with time. So, as this rotates, right, we are seeing it at some point advanced in time. So, is it possible, say from what we are seeing today, can we not backtrack? Can we not close the motion around the Euler plate, reverse the motion around the Euler pole of rotation and make the plates move back? So, if the plates move back, in that case, we would be theoretically able to reconstruct the past position of the plates. So, just as we can actually predict how motion is going to take place at the next instant of time, it is possible for us theoretically, it seems, that we can actually backtrack and find out where the plates were in the past by reversing motion around the same Euler poles with the same velocities. Now, this is just one of my favorite diagrams, not brilliantly drawn, but nevertheless you can see what these are. It shows us the plates as they are today. So, you can see the South American plate and the African plate, whose Euler pole of location we discussed was somewhere, let's say somewhere around here. It would be just south of the Arctic Circle. So, we can see that in different places here. Now, as a consequence of this, can we say, suppose close it around the Euler pole, so between South America and Africa, let us say the Euler pole was somewhere here. I am not exactly sure where it would be, but let us say it was here. If I close it, so if with respect to South America, if Africa is moving, let us say this way, so if Africa is moving this way around this kind of Euler pole, if I reverse the motion around this, so if I reverse the motion around this, can I just go back this way, right, and then close it so that this part of South America fits exactly into Africa as we now think it did? So, that's the question we want to answer. Is it possible to reverse the motions and to find out the past positions of plates precisely simply by reversing the motion that has already taken place around the present day Euler poles of rotation? So, this is the question that would be important. So, framed more more accurately, let's say, or formally, using the method shown in the last class, can we reverse the motion taking place between the present day plates and reconstruct the configuration of these plates hundreds of millions of years ago? Now, this is something I put in deliberately, the hundreds of millions, and that's important because with respect to geological motion, 1 or 2 million years is practically instantaneous, right? In the context that we're using it in, we can make approximations for 1 or 2 million years, considering them to be a very small period of interval of time, which is not unreasonable considering that the Earth is 4.6 billion years old. So, what we are more interested in is that if we try to understand, right, when the situation when South America first broke off with Africa, that would be at least 100 million years earlier. Is it possible for us to reconstruct every stage of that motion, right, and then see how South America linked into Africa by using the present day Euler pole of rotation? Now, so intrinsic to this is something that we need to understand. How do we combine velocities? Suppose, how do we combine angular velocities? Now, just remember what we did before. So, you remember that this is how we operated. So, if we wanted to find out the angular velocity of A with respect to C, what we did was to find out the angular velocity of B with respect to C and added that to the angular velocity of A with respect to B, right? This is how we saw it. Now, this is how angular velocities, right, are added, right, to find out the resultant. So effectively, this is the resultant motion, right? So this is the resultant. We know that this is the resultant of the addition of these two vectors, right? Each of these vectors, just to remind you, in the case of angular velocities, it is a unit vector, right? This indicates the direction of the vector is the direction of the rotation axis, is the unit vector, in this case the positive unit vector, and this rotation angle, this actually specifies the magnitude of the rotation, and it's depicted by the length of the vector along that line. So that's how it's represented. Now, if instead of this, right, we did it the reverse way and wrote it as omega a by b plus omega b by c, this way, right? If we added them in this order, so instead of adding them in this order, we'd essentially get the same result, right? We would get the same result. We should get the same value of omega, right? In this case, we're representing it in a particular manner. So this means, right, the sequence in which you add these two does not matter, and indeed it would not matter for any vectors, because vector addition is commutative. That is, the sequence in which you add doesn't really matter, right? You can add a plus b, you will get the same answer if you add b plus a, right? So vectorially, this is a property that all vectors have. They have a commutative property. Now, this applies, we've applied this to a particular vector that we call the angular velocity, right? Now, the angular velocity is rotation per unit time, right? So technically, it's instantaneous or infinitesimal, right? So it's incremental, instantaneous, infinitesimal, whatever term you choose to use. So angular velocity, right, we can do it. We've seen, we've applied it successfully, and we have been able to identify the Euler poles, rotation of the Euler poles of rotation between all sets of plates. But can we use this to combine two finite rotations? Because we know that if we are going to reverse large scale motion of plates on the surface of the earth over millions of years, we need to be able to see what happens when finite rotations take place. We have to reverse finite rotations. Is that possible? Now, let's just see. We'll have to judge this by looking at what we see when we come across any of the method in which this takes place. So let's actually consider two finite rotations. Let's call one finite rotation, right, is a finite rotation E1, and the second one is a finite rotation E2. Now let's say that finite rotation E1, now this is with respect to you viewing me, right? So we're looking this way. So let's say there is a negative, let's say E1 is a finite rotation which is a negative finite rotation of 90 degrees about a horizontal axis. So if I've got an axis like this, right, so from your side, if you're viewing this, right, so we have a clockwise rotation because it's negative, a finite rotation of 90 degrees. You can actually you can look at it that particular way. From my side, that same rotation would be anti-clockwise. Okay, and let's say this takes place about a horizontal axis. So let's assume that the axis is facing this way. Now the second operation, right, is an operation E2, and we'll say that this is a positive finite rotation, but this is a positive finite rotation about a vertical axis. So let's say the axis is this way. So if I'm looking at it from above, right, so this is related to E2 involves a positive rotation, that is an anti-clockwise rotation of 90 degrees, right, about this vertical axis. So we are actually talking about two sequences of vertical rotations, two types of finite rotations. You can regard them as two operations. Now let's see what happens when we combine these operations like this. So let's say case 1. So I've just taken this from Moose and Twist. It's a beautifully depicted thing. I've just redrawn the figure, and what you can see here is we can talk of two cases. So in the first case, let's talk about E1 being applied first and E2 being applied afterwards. So you're adding, in this case, you're adding E1 plus E2, right? So in this case, what do? So this is this book Tectonics, right, which has tectonics written on it, right? And you're actually rotating it in a around this way. So when you're looking from your side, you actually can see this rotation would be anti-clockwise. From my side, it's a clockwise rotation. So when you rotate this book clockwise, so this is the orientation that it takes up. This is the second stage after a rotation of 90 degrees. Now what I do is to apply rotation vector E2, right? And in this case, when I apply E2, right, let's say it's a positive rotation. So now once it's in this position, so about a vertical axis, I now rotate it positively by 90 degrees. This is the sense in which it rotates, and this would be the final position I land up with, right? So the word tectonics is actually facing downwards, so it's properly read from this direction really. So read from here, so don't get confused from here, right? So you read it from this direction. Now case 2 is a case where we do just the reverse sequence. We reverse the sequence in which we apply the operations. This operation this operation is just the reverse sequence. So we apply E2 followed by E1, right? So it's just the reverse sequence we apply. So in the first case, we start with the same initial position. So the way the book is oriented here is the same as the book where the oriented is here. The starting position is exactly the same. So in this case, what do we do? First of all, we rotate it about this vertical axis. A vertical axis, the same sense, it's a positive rotation of 90 degrees, right, about a vertical axis. So the book rotates from this position. So when I rotate it about an axis like this, so it will automatically rotate, and you can see that it would acquire a position like this, right? So this is what it would be. This would be the position after 90-degree rotation. So this is the second stage in this sequence. Now on this one, now what I do is to apply my second one. So I rotate it, I apply operation E1, which involves this rotation that I am talking about of a clockwise of 90 degrees from my side, anti-clockwise from your side. So it's a positive rotation, right, about a horizontal axis. So this was a vertical axis, this is a horizontal axis. So when I rotate it by 90 degrees around the horizontal axis, now as I rotate it, now you see that this would become the final position of the book. This is the final position in case 2. So this final position, as you can see when I've rotated it, the orientation of the book is now very different from what it was here. So although I started with the same two initial stages, right? When I rotate the book, I find that the final stages, right, are not the same. So the final sequence that I get after adding the rotations E1 and E2 is not the same as the final position that I get when I add E2 to E1, right? So the sequence is reversed. So the end product in the case of case 1 and case 2 are different in these two cases. So the addition of these two finite rotations doesn't appear to be exactly the same as what we see when we add infinitesimal rotations. So the implication is, you see, vector addition, we know by its nature is commutative. Vector addition by its nature is commutative. So in that case, right, why is the addition of finite rotations not commutative? Why is it not commutative? Now this is the catch point here. It's expected to be, it seems to be identical things that we are doing when we are adding angular velocities and finite rotations, and yet I showed you that in the case of finite rotations we cannot apply this, because when we do this we see that the sequence in which we add it, right, is important. It's there. Now this commutative property is not a property just of angular velocities. It's a property of any vector, and it's a necessary property, right? So vector addition is commutative. We all know that. That's one of the basic properties of vectors. Now, if adding finite rotations is not commutative, what it implies is that finite rotations themselves cannot be vectors. So a finite rotation, in itself is not a vector. It has a magnitude. This is in spite of the fact that a finite rotation is associated with a magnitude. A finite rotation is associated with a direction. So in fact we do write, I mean, you'll see many nomenclatures like this. So a finite rotation is written, let's see, okay. So rotation, oops, okay, rotation of E and omega. Okay, so if I write it this way, it means it's a rotation about a unit axis E, unit vector in one particular direction, and omega is the magnitude of that particular rotation. This is exactly how we represent an angular velocity, right? It would be about a unit vector plus an angular velocity omega. We depict it with a small omega. Now, what we can summarize from this is that rotation E1 followed by E2 does not yield the same result as rotation E2 followed by rotation E1. So, the addition of finite rotations is not commutative, right? It means it's not a vector. This was summarized actually brilliantly by Xavier Lapichon, right, who actually showed that this was the case. So, it's a very important conclusion. So, now what this means is that a finite rotation is not a vector. Because it's not a vector, in the case of a vector, for example, if we have an angular velocity vector, right, an angular velocity vector, this angular velocity vector has, say, A about B, you can actually represent it as an angular velocity of AB. So, this is just the magnitude, and you will represent it by its by a unit vector, let us say a unit vector E, right, or rather the unit vector would be stated first followed by the angular velocity. This is how conventionally it's better to write it this way. So, let me just simplify this a little bit and write it properly. So, you can actually write it as a unit vector this way, right, with the angular velocity of A by B, right. So, this is what you have. So, this is how we depict vectors. Now, in the case of the rotation vector, now what this means is this is equivalent to a rotation in the direction of the unit vector depicted by this depicted by E here, and the magnitude is given by the magnitude parallel to that. So, we actually have a magnitude of omega AB, right, parallel to that unit vector. In the case of a finite rotation, however, while this is there, this omega is not parallel to the unit vector. You cannot depict it as its magnitude as a line which is parallel, as the length of a line which is parallel to the axis of rotation depicted by the unit vector, because this itself, rotation itself, is not a vector. So, a finite rotation is not a vector. That is important, and because that is the case, it's not commutative. And that is what Xavier Lapichon pointed out. It's an old principle, but nobody had ever thought of it in the context of plates before. Now, what consequences does this have? Now, how does this apply to movement on the Earth? So, again, I've taken this from Moores and Twist, and it's a lovely little diagram. We've redrawn it from there. So, we can actually just represent it, right, in the form of, let's say, Euler poles. So, let's say there are three plates. So, this is plate A, right, and let's say plate A remains fixed throughout whatever we're talking about. So, this is plate A. So, plate A on this side remains fixed throughout its motion. Now, as plate A, with respect to plate A, it's a ridge triple junction. So, plate B, which is along here, so this is plate B, right, and this is plate C, so on this side. So, plate B, right, with if we consider plate A to be fixed, plate B will move with respect to plate A about this Euler pole of rotation, which is the Euler pole of B with respect to A. So, B will rotate with respect to plate A about this Euler pole, right, and it will keep on moving, and its position will change from position B1, where its original position, to position B2 this way, to position B3, to position B4, and we can say that at some point in time, right, it will be at this position P5, right. So, this point was once out here, now it's way out here, right. So, it's actually moved away, and this is what plate B looks like after sufficient movement here. On the other hand, let's take this particular part here, plate C. Plate C does the same thing. It moves away with respect to plate C, and its movement is about this particular Euler pole. Now, both of these Euler poles, B with respect to A with respect, these are fixed with respect to plate A, and this Euler pole is fixed with respect to both B and A. This Euler pole E is fixed with respect to both A and C. Now, at the initial instant of time, let us assume that this position, this is the Euler pole location of between plates C and B. So it's the instantaneous Euler pole of rotation that we see here, and its counterpart just on the opposite, you can say on the other side, is here. So this would be the Euler pole of rotation, right? This is what we actually see for B with respect to C. Now, there is something that is unique here. When rotation takes place about an Euler pole, so we can just actually go to the next diagram just to see this. So when rotation takes place, right, about say here or with respect to here, so what happens is plate A is fixed. So let's say, so roughly this is plate A. Now forgive my bad drawing, right, but this is roughly the position of plate A, and this is roughly the position of the the original position of plate B, original position of plate C. So this is A, B and C, and we've got this Euler pole here, right, and we've got this Euler pole here. So this is the Euler pole of B with respect to A, this is the Euler pole of A with respect to C. So these are two different Euler poles, and we can just think of the instantaneous Euler pole of C with respect to B, right, located out here. Now in this case, you see, whenever something is rotating on the surface of a sphere, right, so the position of the pole, so if I keep one point is fixed, with respect to that point, there is only one other point in the entire sphere which remains static. There is only, or rather 2 points which remain static, and these are the Euler poles of rotation. So if I keep one part stable, right, as I now rotate about it, and if I consider one plate to be fixed, right, then with respect to this, only one Euler pole of rotation, the location of only one Euler pole of rotation is going to remain fixed. There can be only one point, in fact, on the entire sphere, surface of the sphere, or 2 points, one this Euler pole and the other Euler pole. The two Euler poles would be the only 2 points which would remain fixed with respect to the fixed plate, right, on rotation. All other points on the sphere will tend to rotate. Therefore, when this takes place, you see, this part here, this segment here, this is the Euler pole rotation location of C with respect to B, of C with respect to B. This point itself is not, it doesn't, when B is rotating with respect to A, this is just another point on the sphere. So this would also tend to rotate with respect to this Euler pole of rotation. So plate A is fixed. With respect to this, I fixed the position of the Euler pole here. So even though I fixed it here, there is no way that I can keep this Euler pole or this Euler pole fixed with respect to both plates B and A. There can be only those 2 points. With respect to plates B and A, only the two Euler poles of rotation corresponding to their motion on the sphere will remain fixed on the surface of the sphere as there is some rotation. On the other hand, right, with respect, the same applies to C with respect to A. So this can be possible. We can keep these, if we consider this and this, this and plate A to remain fixed on the surface of the sphere. In that case, it is in no way possible to keep this particular Euler pole, which is another point on the sphere, fixed with respect to plate A or these two Euler poles of rotation. It will necessarily move. And what will happen is that with respect to plate B, right, plate B and plate C, so you can imagine the point here. So if I put the point here, that is the present day location. So working back from points from B5 to here, so plate B with respect to plate C will move along move somewhere like this, and this would move plate B would move somewhere like this. Ultimately, this point would converge at its present day position. So these would depict the past positions of the Euler pole, of this Euler pole, right, with respect to plate C. This would be the past positions with respect to plate B. So ultimately it converges. The present day position is where we are seeing it. This is the instantaneous point, and this is something that we can correlate with. Now, this means then, you see, once again, that within the Earth, we cannot actually reverse finite rotations to get back at the past positions of plates. Now, we talked about finite and infinite in terms infinitesimal or incremental, in terms of, or instantaneous in terms of the Earth. So geologically speaking, what is instantaneous? So it's actually maybe the Euler poles that we see today, right? The whole table I showed you of the Euler poles of rotation for the angular velocities that we showed today, that could that would probably only be valid for maybe a couple of million years or so. If we go into tens of millions of years, that's absolutely stretching, and already the positions of the Euler poles would begin to migrate. So it would appear that the Euler poles are actually moving. So there'd be a new position of the Euler pole, say for South America and Africa, right? Say 10 million years ago. So the Euler pole 20 million years ago, 40 million years ago will not, between South America and Africa, will not be the same as the Euler pole location that we see today. So therefore, they're also moving. Because of this, people have continuously tried to think of or define movement in terms of absolute motions. Okay, and now that is different, especially when plate tectonics, all these details were being worked out in the 60s. We didn't have that many satellites, and it was not possible to monitor these so well from outer space. So we needed a fixed frame of reference, right? And what was thought of is to use a frame which corresponded to something inside the Earth, but which was not linked to the plates. And these are called hotspots. Now, on the Earth's surface, we know that there are most volcanoes are associated with plate boundaries. We discussed that that was how the whole theory was slowly built up. However, there are some volcanoes which are very active, which lie within plates. These are called intraplate volcanoes. And we think that these intraplate volcanoes actually correspond to melting from some place which is much deeper than the plate itself. So it would, most of this hotspot melting takes place at depths of say 150 to 200 kilometers or so. And in fact, we believe that these hotspots result from parts of the lower mantle, either detached from the core mantle boundary or from the lower mantle upper mantle boundary, which migrate as a solid into the upper mantle. They rise very fast into the upper mantle, and they melt at depths of around 150 to 200 kilometers, well below the present day lithosphere of either the oceanic plate or the continental plate. So as a consequence, when the plate moves on top, you begin to see these lines of volcanoes, and this is what was used by Tuzo-Wilson to identify the rigidity of plates. Now these are the famous ones that you can see. So the idea here is that you can see that these define hotspot trails, and one of the most famous ones is in the Pacific. This is Hawaii. This is called the Hawaiian Seamount Chain. This is called the Emperor Seamount Chain. The oldest volcano in this chain is somewhere around here, and the one that is currently active would be somewhere around here. So what we have here now, it means then that as we work back, you can actually see that the plates are moving with respect to the hotspots. Therefore, the idea that was used was to use what is called a hotspot reference frame for monitoring how motions take place. So these were considered, motion with respect to hotspots was considered to be an absolute motion. That's what people categorized it. And then when you actually follow the trajectory of plates, you see that most of these plates actually show this kind of trajectory. So this is actually defined by the hotspot trails, but in effect they're pointing out the directions in which the plate moved. Now in Hawaii, as you can see, this is around 43 MA. Okay, so this is around 43 MA. Coincidentally, actually, even here, the one which the reunion hotspot, right? This is also around 44 MA is when you actually begin to see this peak. 44 to 43, I forget the exact thing, but it's around the same time that you see a kink here. So there is a change in relative plate motions, and this tells you that something has changed, right? The directions of the plates changed as given by the inflection points on the hotspot trails. So the inflection points, inflection points on hotspot trails tell you that that particular plate must have changed its absolute direction of motion. Okay, so it's something that is of great use to us, and we can actually monitor how plates move. Now, what was done, this is actually modified from Moose and Twist, who actually based this data from things taken elsewhere. So with respect to a hotspot trail, people tried to actually find out what the velocities of the would be at various points within plates, and this is what they landed up with, right? So along various kinds of boundaries, this is the sort of absolute motions that you can work out, right, with respect to a hotspot frame. So as you can see that the motions, they are not absolutely perfectly straight everywhere. We have to make allowance for some parts at the top which is distorted, but nevertheless, in general, we can see that in a hotspot reference frame, that the plates are moving at every point on the plate. It seems to be moving in the same direction. So together, what this means is that we can conclude from whatever we've discussed today that finite rotations themselves are not vectors, and therefore their addition is not commutative. One can argue the other way, that because their addition is not commutative, you cannot regard finite rotations as vectors. So you can actually not reconstruct past plate motions, right, more than say a few tens of millions of years, if you reverse the motions around present day Euler poles. So it means then, just knowing the positions of the present day Euler poles and the angular velocities today, we cannot work back and find out exactly where the plates were in the past, how the plates have moved. We need something else. We need some more information. This basic geometry, all that we've done so far, is not enough. How do we do it? And we'll see that we have a technique. So these are the references that you can broadly follow. This is, I've also mentioned Le Pichon's paper here. So it's it's a book in which he's actually documented what he was talking about. We'll talk about it next class.